Imagine discovering a planet that is literally dying in front of our eyes. Not because it collided with another world, not because it ran out of energy, but because the very star that gave it life is now slowly ripping it apart, piece by piece. Every single orbit, this distant world loses more of itself into space. Rivers of molten rock escape its surface. A gigantic tail of dust stretches behind it like a cosmic comet. And with every pass around its star, the planet becomes smaller than it was just hours before. For decades, astronomers believed planets were relatively stable objects. They formed, evolved, and sometimes disappeared only after billions of years. But then, telescopes spotted something no one expected. A planet that wasn't simply orbiting its star, it was evaporating, and humanity happened to catch it in the final moments of its existence. The story begins nearly 1,900 light-years away in the constellation Cygnus. Back in 2012, NASA's Kepler Space Telescope was doing exactly what it had been designed to do, searching for tiny dips in starlight caused by planets crossing in front of their stars. Most planetary transits look almost identical every time. The planet blocks the same amount of light, the transit lasts the same amount of time. Everything is beautifully predictable. But one star refused to follow the rules. Cataloged as KIC 12557548, it displayed a bizarre signal. Sometimes the star dimmed by more than 1%. Other times, almost nothing happened. The depth changed dramatically from orbit to orbit. At first, researchers suspected instrumental errors. Maybe Kepler had glitched. Maybe background stars were interfering. Maybe something was wrong with the data. But as more observations arrived, the strange pattern continued. Something real was happening, and nobody knew what. Then, scientists noticed another detail that made the mystery even stranger. The object completed one orbit every 15.7 hours. Not days, not weeks, hours. That meant it was unbelievably close to its star, far closer than Mercury is to our sun. At that distance, temperatures were estimated to exceed 2,000 degrees Celsius, hot enough to melt rock, hot enough to vaporize entire mountains. Suddenly, a shocking possibility emerged. What if this wasn't an ordinary planet? What if the intense heat was literally turning solid rock into gas? The idea sounded almost impossible, until computer simulations matched the observations with astonishing accuracy. The strange, changing transit depths weren't caused by the planet itself. They were caused by a massive cloud of dust surrounding it. The planet was shedding material into space, like a candle melting beside a raging fire. Except this candle was the size of a planet. Astronomers had never seen anything like it. The object soon became known as one of the first confirmed disintegrating planets. But how can an entire planet simply fall apart? The answer lies in a brutal combination of gravity, heat, and time. Unlike Earth, this world orbits so close to its star that 1 year lasts less than 16 hours. Imagine watching over 500 New Year's celebrations before Earth finishes one single orbit around the Sun. Each orbit exposes the planet to relentless stellar radiation. Its surface isn't covered with oceans or forests or ice. It's believed to be covered by vast oceans of molten lava. Liquid rock stretches across enormous regions of the planet. The heat is so intense that minerals normally locked inside mountains begin to evaporate. Elements like sodium, magnesium, silicon, and iron escape into the surrounding space. As these materials drift away, they cool into microscopic dust particles. Radiation from the nearby star then pushes this dust outward, creating an enormous tail that trails behind the planet, exactly like the tail of a comet, except comets are made mostly of ice. This tail is made from the remains of an entire world. Every orbit, more rock escapes, more dust forms, more of the planet disappears forever. Estimates suggest the mass loss could reach tens of thousands of tons every second, numbers that sound unimaginable, yet on planetary scales, they're entirely possible under these extreme conditions. If the process continues long enough, the planet may eventually vanish completely. As astonishing as that sounds, the mystery had only begun, because astronomers soon discovered KIC 12557548 wasn't alone. Another strange object appeared around a different star. This time, observations from multiple telescopes revealed a remarkably similar phenomenon. The planet known as KOI 2700b also displayed signs of disintegration. Again, transit depths varied. Again, a dusty tail explained the observations. Again, a rocky world appeared to be slowly evaporating. Then, another candidate emerged, and another. Suddenly, scientists realized this wasn't a one-time cosmic accident. Nature had created an entirely new class of planets, worlds caught during the final chapter of their existence. For planetary scientists, this was revolutionary. Until then, researchers mostly studied planets after they had settled into long-term stability. Now they could actually witness planetary destruction in real time. Instead of reconstructing ancient history from surviving worlds, they could watch geology unfolding live across interstellar distances. But one enormous question remained. How do you prove that a planet is actually losing rock? After all, no telescope can directly photograph a tiny planet nearly 2,000 light-years away. Researchers needed indirect evidence, and they found it through light. When starlight passes through gases escaping from a planet, specific chemical fingerprints appear in the spectrum. These fingerprints reveal which elements are present. Several observations hinted at materials consistent with vaporized rock. Although difficult to detect because the dust clouds constantly changed, the evidence increasingly supported the idea that minerals from the planet itself were escaping into space. Every observation strengthened the case. This wasn't dust from asteroids. It wasn't leftover material from planet formation. It was the planet. The realization transformed these worlds into natural laboratories unlike anything in the solar system. Earth cannot teach us how planets die this way. Neither can Mars, nor Venus. Nothing in our neighborhood experiences temperatures high enough to vaporize entire landscapes continuously. These distant worlds allow scientists to study rock behaving almost like water, mountains becoming vapor, lava becoming atmosphere, atmospheres becoming tails stretching hundreds of thousands of kilometers through space. Its planetary physics pushed to the absolute limit. Then another surprise arrived. Scientists realized the escaping material wasn't leaving uniformly. Powerful stellar winds interacted with the dust. Magnetic fields influenced particle motion. Radiation pressure stretched the cloud into asymmetrical shapes. This explained why every transit looked slightly different. The dust tail itself was constantly changing, like smoke blowing in unpredictable winds. Sometimes the cloud became thicker, sometimes thinner, sometimes longer, sometimes shorter. Every orbit painted a different picture. For astronomers, this variability became a goldmine of information. Instead of seeing a repetitive event, they were watching an evolving disaster. Each transit carried new clues about the planet's interior, its composition, and the violent environment surrounding it. And then researchers asked an unsettling question. If stars can destroy planets this efficiently, could something similar ever happen closer to home? The answer wasn't as comforting as many expected. Our solar system appears safe today, but stars change dramatically over time. Billions of years from now, our own sun will expand into a red giant. Mercury will almost certainly disappear. Venus will likely be consumed. Earth itself may not survive. Entire planets could eventually be swallowed, melted, or stripped apart. In other words, these dying worlds aren't just distant curiosities. They're windows into the possible future of countless planetary systems across the galaxy, including, eventually, our own. But just when astronomers thought they understood
The idea sounds almost unbelievable. A planet isn't just a giant rock floating through space. Its gravity acts like an invisible shield, constantly pulling everything toward its center. Every mountain, every ocean, every grain of dust remains attached because gravity is stronger than anything trying to pull it away. But gravity has limits. Move a planet close enough to its star, and eventually another force begins to compete. That force is called tidal gravity. You already see a gentle version of it on Earth. The moon's gravity stretches our oceans, creating high and low tides every day. Now, imagine replacing the moon with a star. Not millions of kilometers away, but so close that it fills a huge portion of the sky. The side of the planet facing the star feels a stronger gravitational pull than the far side. Instead of simply raising tides in water, the star begins stretching the entire planet. Solid rock flexes. The crust cracks. Deep underground, magma is forced upward. Over thousands and perhaps millions of years, the world's interior becomes increasingly unstable. Scientists believe this constant stretching helps fresh molten rock reach the surface, where temperatures exceeding 2,000 degrees Celsius immediately begin turning it into vapor. It's a devastating feedback loop. The star heats the planet releases material. As it loses mass, its gravity weakens. Weaker gravity allows even more material to escape, which weakens gravity even further. The destruction slowly accelerates. It's like punching tiny holes in the hull of a ship. At first, only a little water leaks in, but the damage grows until the ship can no longer save itself. Astronomers believe these disintegrating planets may have once been much larger than they are today. Some models suggest they could have started as worlds several times more massive before losing enormous amounts of material over time. That means the dying planets we observe today may simply be the tiny surviving cores of much larger ancient worlds. We are not witnessing the beginning of their story. We are witnessing the final chapter, and perhaps the last few pages. Then another extraordinary discovery expanded the mystery even further. Using increasingly sensitive instruments, astronomers realized that not every dusty tail behaved the same way. Some tails stretched behind the planet, others appeared slightly offset. The differences weren't random. They depended on the size of the dust particles, the strength of the stellar radiation, and even the composition of the vaporized minerals. Tiny particles behaved almost like smoke caught in a hurricane. Larger grains resisted the stellar wind longer before drifting away. By modeling these motions, scientists could estimate what kinds of rocks were evaporating, even though they could never directly touch or photograph the planet itself. In a remarkable way, they were performing geology across nearly 2,000 light years. Imagine identifying the minerals inside a distant world using nothing more than faint changes in starlight. Just a few decades ago, that would have sounded like science fiction. Today, it's a real branch of planetary science. And the technology keeps improving. When the James Webb Telescope began studying exoplanets in unprecedented detail, astronomers gained an entirely new way to investigate extreme worlds. While Webb hasn't directly imaged these tiny disintegrating planets, its powerful infrared instruments are transforming our understanding of scorching exoplanets, atmospheric chemistry, and mineral-rich environments. Each new observation helps refine the models scientists use to explain planetary evaporation. Every improvement brings us closer to understanding exactly how rocky worlds die. But the implications extend far beyond a handful of strange planets. These discoveries forced scientists to rethink planetary evolution itself. For years, researchers assumed that once a rocky planet formed, its size remained relatively stable. Now they know that isn't always true. Some planets continue changing dramatically long after formation. Entire worlds can shrink, their surfaces can be disappeared, their atmospheres can be rebuilt or completely erased. The universe is far more dynamic than we once imagined, and in some solar systems, planets may spend millions of years slowly dissolving into space before finally vanishing altogether. Then came another surprising realization. These planets don't simply teach us about destruction, they may also teach us about creation. Every atom escaping from a dying planet enriches the surrounding space with heavier elements: silicon, iron, magnesium, calcium, the same ingredients that make up Earth's mountains, buildings, and even our own bones. Those materials eventually mix with interstellar gas and dust. Much later, they may become part of entirely new stars, new planets, perhaps even new life. In an extraordinary sense, the death of one world may help build another. Astronomy often reminds us that destruction and creation are inseparable. Stars explode to create the elements needed for planets. Planets erode to seed future solar systems. Nothing in the universe remains unchanged forever, not even worlds. But perhaps the most fascinating lesson isn't about physics, it's about timing. Human civilization has existed for only a few thousand years, modern astronomy for just a few centuries, yet during this tiny slice of cosmic history, we happen to develop telescopes powerful enough to witness one of the rarest planetary events ever observed. Had intelligent observers appeared 10 million years earlier, the planet might have looked perfectly ordinary. 10 million years later, it might already be gone. The odds of catching a planet during this brief disintegration phase are incredibly small, yet we found multiple examples. That suggests either we have been extraordinarily lucky, or these events are more common throughout the galaxy than anyone expected. If it's the second explanation, then countless planets may currently be dying across the Milky Way. Right now, as you watch this video, invisible to our eyes, slowly disappearing into the darkness. Researchers are now searching for many more examples using missions like TESS alongside ground-based observatories spread across the world. Every new candidate helps scientists answer fundamental questions. How quickly do planets evaporate? How massive must they be to survive? What minerals escape first? How does stellar activity influence the process? Can entire categories of planets eventually disappear without leaving obvious traces behind? Each answer creates new questions. That's the beauty of science. Every discovery opens another door. The more we learn about these doomed worlds, the more we realize how diverse planetary systems really are. Some planets are covered in global oceans, some rain molten iron, some wander through interstellar space without a star at all, and some slowly dissolve into cosmic dust while orbiting the very star that once formed them. It's a reminder that our own solar system is only one version of what nature can create, not the standard, not the rule, simply one possibility among hundreds of billions. Perhaps the greatest mystery isn't why these planets die, it's why they survived long enough for us to find them. Some have likely endured unimaginable conditions for millions of years before entering their final unstable phase. Others may disappear much sooner than current models predict. Future observations will decide which theories survive. As more powerful telescopes come online over the coming decades, astronomers expect to discover even stranger worlds. Planets with exotic chemistries, extreme weather unlike anything in our solar system, and perhaps entirely new methods of planetary destruction that we haven't even imagined yet. Because every time humanity believes it understands the universe quietly reveals another surprise. A planet turning into a comet, a black hole awakening after decades of silence, a signal traveling billions of light years, or a distant world that refuses to die all at once, instead surrendering itself grain by grain, orbit after orbit, until nothing remains except a fading trail of dust illuminated by a relentless star. Somewhere nearly